All right, so next time we're going to kind of talk about a pretty groundbreaking idea, and that's the particle nature of light. So we talked about light as a wave previously, and for the longest time, light was thought of as solely being a wave. So for a long time, light was thought of as a wave, right? Light's a wave. The issue with that is that if you treat light as just a wave, there's a number of properties that can't be explained. So this is just one example of, you can take a look at the internet or your book for some more examples, but one example of this is the photoelectric effect. The photoelectric effect is basically what powers solar cells. So if we think about kind of in terms of green energy and kind of the new wave of energy, obviously this is an important idea. And so what we have here is a metal, and basically if you shine the right type of light on certain types of metals, they will dislodge electrons. So basically you can then gather these electrons and thus produce electricity. This is basically how solar cells work. And so they did a number of experiments. So one thing they did is they shot red light at it, so 700 nanometer light. And then what they saw was nothing happens. Nothing happened. No matter how long you put the light on here, there's no electrons. So they try to increase the intensity, right? Oops, probably shouldn't draw like that. Kind of the same nanometer, but increase the intensity. So still 700 nanometer, but just increase the intensity. And again, they saw nothing. So no matter how long you do it, you don't get any electrons. And if light is a wave, that doesn't make sense, because you should be able to shine light on something and then it should build up that amount of energy. And then when you've shown enough light on it, it should eject an electron. So another thing they tried to do is to shorten the wavelength. So they shot it with 400 nanometer light, which is something like violet light, and out popped an electron immediately. And so then they tried to increase the amplitude of the light, but still 400 nanometer wavelength. And what they saw was more electrons. More electrons, right? So here we get electrons immediately. So no delay. And as we increase the amplitude, we increase the number of electrons, And so what Einstein said, that the only way this could be true is if we think about light as a particle, not a wave, because a wave should be able to build up energy, while a particle simply does not have enough energy to do so. So instead of thinking about light as a wave, Einstein said that light can be thought of basically as a particle. So there's a little particle of wave, and when you shoot this at the metal, the particle simply does not have enough energy to dislodge the electron. Whereas when you try a shorter frequency of light, this particle now has more energy, and thus you're able to kick out an electron. And so these were eventually called photons. So photons are particles of light. And when we're talking about photons as particles, we can see a certain thing here. So the wavelength of light corresponds to the energy of the light, which is something nowadays we accept as true, but back in the day, that was a much more controversial thing. And then the amplitude, we can think of the amplitude as just the number of photons. So for example, if we went from kind of this to something like this, you can think of this as one photon versus maybe like 2 or 3 photons. And so this is what Einstein actually won his Nobel Prize for. He said that the energy of light is equal to hv. So this is energy. This is Planck's constant. And it's 6.626 times 10 to the negative 34 joule seconds. And then this is frequency. So we can say it this way, or we can swap out frequency for wavelength, so equals hc over lambda. Or I'm just going to label the new things, right? This is wavelength. And then this over here is the c is the speed of light. So this is what Einstein actually won his Nobel Prize for. And it's basically this wave particle duality. So what this means is that when we talk about very small things, they can behave as particles or waves, right? It depends on the specific experiment. There's experiments that show light behaving as a wave, and there's experiments showing light behaving as a particle. And so this is something we don't see in the macro world. Things are either particles or they're waves, but when we get to really small things, they can be either or, right? Sometimes a wave, sometimes a particle, right? And so this is a pretty nuts idea, pretty crazy idea, you can see. This is a quote from Einstein. He says that it seems as though we must sometimes use sometimes the one theory and sometimes the other, while at times we may use either. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomena of light, but together they do. And so what he's talking about here is the wave and particle duality of light. So this one says by Einstein. It is actually kind of a pretty complex topic and requires some kind of higher level knowledge that we haven't accumulated yet. So if you don't really understand how this causes light to be both a particle and a wave, you can try to Google the internet, try to find some fun videos about it, but overall, don't worry about it too much. Just know that light can be a wave or a particle.